All right, so people are still having trouble with Pearson?
No, I got it.
Okay. Pearson is acting very strangely. Like sometimes the courses aren't appearing on people's accounts too. But then if you go to your profile, it'll ask you to log in again and it'll appear. So I don't know. I don't know what Pearson's doing. They're making me upset. I asked them like, hey, you gotta give me someone I can go to directly to solve all these problems, and still nothing. But oh well. I'm trying. I don't have any authority in Pearson. I'm just merely their customer. But so is anything cool? Anybody have anything before we start? Nope, nope. Okay, so in the chapter 1 stuff, and we're recording right now, just so you know. So I'm going to post this to Lalima later. But let me start off with chemistry. Chemistry, I mentioned this before, I think. Chemistry is studying matter and its changes. So chemistry is studying matter. Before I go on, has anyone ever heard of dihydrogen monoxide before?
Yeah.
Yeah. Yeah, it's a killer. It's important that we ban it, right? It's a chemical. DHMO is a chemical. It's a very powerful greenhouse gas, set to cause about 80% of global warming. So it's what's behind climate forcing. So if you know the theory of anthropogenic climate change. It was in the Fukushima nuclear plant. We find it in cancer cells. We use it extensively in animal research, and there's a huge investment for its use in warfare. Can you think of any other reasons why we should ban it if you're familiar with it?
Take too much, people die.
Oh, absolutely. 100% correlation. Anyone who takes it dies. So, there's a little bit of a joke here, if you haven't noticed. Dihydrogen monoxide is H2O, it's water. So, using a word like chemical, everything's a chemical. If it's made of atoms, it's a chemical. Air is a chemical, water is a chemical. We're chemicals. Well, I mean, we're mixtures of chemicals, right? So the word chemical is even used very incorrectly, or at least it strikes fear. Like, does this have chemicals? Like, yeah, I hope so, you know? But, okay, so everything I said was true. Water is a greenhouse gas. It's a very powerful greenhouse gas. It is the greenhouse gas for the Earth. Has anyone ever been to a desert before? What's it like during the day? What's it like at night?
Cold.
Yep. So without water, that's what the Earth is like. So the Earth's average temperature would be around -15 Celsius, 0 Fahrenheit without the greenhouse effect. We're at about average temperature about 15 degrees Celsius. So we have a plus 30 degrees Celsius greenhouse effect. And we have a much more temperate climate with the water. And that's the idea behind climate forcing. Carbon dioxide is a pretty weak greenhouse gas, but the idea is that it evaporates more water, and water is what does the global warming, not the carbon dioxide itself. It's used in nuclear power plants. Yeah, you find it in any cell. Used in animal research. This is all true. And has anyone ever heard of the Navy before? Right. So everything here is true, but it has a negative spin on it. So that's one of the reasons why to study science, is so that you can't be fooled by some of these things, people say. And we jump around topics quite a bit in the beginning. I do apologize for that. That's just up until about that second part of chapter 3, then we start to kind of move a little more forward at a more logical pace. Now we just jump around quite a bit, so bear with me if you don't mind. And I'm going to talk a lot today. So I'll probably talk a lot next lecture too. Oh, Monday's a holiday. So hopefully you remember that. Monday is a holiday, but Wednesday we'll talk about atoms. Or at least next week we'll talk about atoms, and then we'll get into more logical train of good old chemistry. But this is the beginning, and I assume I have a couple of students in the other class. They had never had a chemistry class before, so I'm making sure to start from the beginning. And starting at the beginning is science. So can you guys read this in the back? Is this too hard for you to read? No, you can. You're squinting. Can you?
No, I'm fine.
I can zoom in. So science, so definition of science, science is a systematic approach to solving a problem. You're saying like, I'm doing this, this is a science, I'm doing it scientifically. What do you mean? You're doing it systematically. It's a systematic system, and then the scientific method is what science uses. So let me go back and talk a little bit about sciences. We kind of say there's the big three sciences: biology, physics, and chemistry. There's others. There's oceanography, there's geology, that kind of thing. So oceanography is study of the oceans, geology is study of the earth. Biology is a study of life. Physics is the study of the physical world. To me, that's how long the vector is and where it points. So I have my center of mass is about right here, and it's pointing straight down towards the center of the earth, and the floor is pushing back with a normal force equal to my weight. That way I'm not sinking through the floor. So that's physics. It's like how long the vector is and where it points, to me. Chemistry studies matter. And types of chemists, there's synthetic, physical, and biological. So most chemists are synthetic chemists. They're the chemists that make things. Physical chemists, these are kind of the halfway between physics and chemistry. That's me. I'm a physical chemist. And frequently physical chemists are the ones that teach general chemistry as well. So if you like Breaking Bad, Heisenberg is more of a synthetic chemist. If you like the Big Bang Theory, I'm more like Sheldon with vacuum chambers and lasers and that kind of stuff. So that's the kind of chemist I am. And biological, this is an emerging field where biology and chemistry intermix. And chemistry is also very intimately tied to mathematics as well. I use a lot of different symbols. I'll show you some of them later on. If you see a symbol, you don't understand what it means, ask me and I'll tell you. I'm trying to be cognizant of that as I go through and show you the symbols. Because that's one of the things taking this class is you want to be like, okay, I understand what that symbol is. The symbol I'll show you later is capital delta is for change. But you'll see some of that as we go through. Okay. So scientific method, it's the method, the approach. This is a systematic approach science uses. And we can start off with observations. So starting out with observations. This is not a very good screen. Is this bothering you how much I'm zooming in, or I'm trying to get so it's easier for you to read? So starting with observations, it's down here, you can't see it, but I have. So quantitative and qualitative are the two types of observations. So quantitative, quantity, number-based. A quantitative observation is number-based. A qualitative is an idea-based. So there are 3 people sitting in this desk. That is a quantitative observation. So this is a small classroom. Qualitative, that's an idea-based. So that's the difference in that. So observations, if you gather enough observations, you can form a scientific law. A scientific law is a summary of observations. So, and they can be simple, like the law of gravity. The law of gravity is what goes up must come down. So I can do this all day, and I can verify the law of gravity. That would be a very boring class, right? So scientific laws can be equations. So we're going to use the ideal gas law later. That's pressure times volume equals number of moles times the gas constant times the temperature. PV equals nRT. Or Newton's second law, force is equal to mass times acceleration. So can you break scientific laws? Yes, you can break them. Law of conservation of mass, that's a law. Matter is neither created nor destroyed. Can you break that? Yes, you can. Nuclear reactions breaks that. So, okay, well, let's go more to scientific method. Observations, you can form a hypothesis. A hypothesis is an educated guess, and then if enough experimentations then test the hypothesis, if enough experiments and observations verify a hypothesis, the hypothesis becomes a theory or a proven fact. And to give you a real simple example, let's say my car doesn't start. So I try to start my car, it doesn't work. I'm like, okay, my observation is my car doesn't start, I'm hypothesizing that I'm out of fuel. So I can experiment, I put more fuel in the car, and I try to start the car, and the car doesn't start. So, all right, it's not the fuel. Maybe my battery's dead. And get someone to jumpstart the car. It works, okay. The experiment has confirmed the hypothesis. The theory is now my battery's dead. Of course, that's a real simple example. Theories are usually a little bigger, like atomic theory, the idea that matter is made of atoms. Also things like germ theory, that illnesses are caused by pathogens and not evil spirits or bad air. So that is an example of a theory. And theories can also be wrong, and they can also be incomplete. So germ theory does not explain every illness. There are illnesses like mental illnesses, cancers, and occupational illnesses like contact dermatitis, that's forever inflamed skin. That's not from any diseases. So there's limitations to theories. So, oh, and this capital sigma is sum. That's a sum. So if I have the notes here, quantitative. So theory is a proven fact. And theories can be, and often are, wrong. So we know that there's things wrong with our theories right now. In physics right now, we have two theories that describe everything. We have quantum mechanics that describes everything that happens on an atomic level. And we have general relativity that's really good explaining things that happen like in space with planetary movements. We can't bridge the two. So we can't start off with protons, neutrons, and electrons and come up with the orbit of Mercury, for instance. We can't do that. There's a couple contenders. One of them is string theory. So string theory is not a scientific theory. It's actually really a hypothesis because it's not been experimentally proven. String theory is a theory by math. It's a mathematically proved theory. There's also several string theories. They have not been proven experimentally. Until string theory can be verified experimentally, it's not considered to be a scientific theory. So it really should be the string hypothesis. But if string theory is proven experimentally, quantum mechanics and general relativity are out. And string theory is now the new dominant theory. And so science is tentative. So this is a big thing. Science is tentative. If anything is wrong, then it's the theory provides, but the experiment decides. This has been a big change in about the year 1850 or so. Also, we've sometimes referred to this as the Age of Enlightenment, that we base our science off of experiments instead of philosophy. So saying that this is the way it should be, the way things should be, is no longer valid. Like we've had a lot of scientific theories, but not by contemporary standards. But like I mentioned illness, there was another theory that the body has 4 humors, the phlegm, blood, green, and yellow bile. And if you're sick, it's because one of them is not in balance. So you have a cold, you have lots of mucus, all right, let's bleed you, and we'll get your humors back in balance. Or you just need to get rid of that phlegm, so here's a bucket, just spit all your phlegm. When you spit all your phlegm, you'll be well again. That's how you cure a cold, which, I mean, actually works, right? Because if you get rid of your phlegm, then your body will have time to get over the cold. So, I mean, the theory predicted the right thing. Hey, you got rid of your phlegm, you're back in order, right? So theories, even when they're wrong, they can still predict the right thing. So, but a big mistake people make is correlation does not equal causality. So correlation does not mean causality at all. One of a famous example, has anyone ever read the book Freakonomics? No, okay, that's a fun book. Okay, I like the book. But in there they talk about, so polio outbreaks. There were some polio outbreaks. They noticed that there was a very good correlation between ice cream sales and polio outbreaks. That when ice cream sales went high, lots of kids got polio. And so the take-home message was, parents, stop buying your kids ice cream because they might get polio. No, the reason why they matched was what's called a common third factor. So when the weather is warm, people intermix more. And when people intermix more, there's more diseases. Communicable diseases spread more quickly that way when there's more interaction. And here in Hawaii, it's always warm, but like in the East Coast of the United States, for instance, it's cold in the winter. People tend not to go out as much. They tend to stay in their homes. And when summer comes along, you go outside and you interact and you play more. And then because of that, there's more diseases. So correlation does not mean causality. There's a whole website with this too. That's kind of fun. There's also a website for banned DHMO. So if you're bored and you want to look at something. And science is really powerful. As I work, sometimes I look at Netflix shows. I'm sure I'm not the only one, but there was one about how people have been put away due to bad forensic science. So people go to jail for bad forensic science. And so here's an idea of some bad science. Has anyone ever heard of the theory of eugenics? So some people have. Yeah, it was. This was a theory. Some people still believe this, but that there's different races of humans, and the human race will go extinct due to inferior genes. This was a law. Mostly it was white people. White people were considered to be superior. This doesn't matter, and I gotta watch out being recorded. I would be one of the most perfect specimens because I'm Nordic, I'm blonde hair and blue eyed. So I would be considered to be the most advanced human. Of course, that's utter BS, and I already mentioned last class, my wife is Asian, right? So, and we even use the word race. Like, what race are you? Like, human, right? I mean, there's really only one race right now, and it's the human race. Because to be the member of the same natural species, if you produce an offspring that's fertile, then the two members that engaged in that are the members of the same species, or the same natural species. I mean, of course, the lines can be a little blurred. You know, like, does that mean we're the same species as Neanderthals? Because, I mean, I did a 23andMe. Apparently, I've got some Neanderthal DNA myself. So I guess we all do. But I mean, so there is a little bit of leeway with that. But I mean, we're all humans, and the idea that we're different races is complete nonsense. You could maybe argue that we have subspecies of humans, but even that is really, we don't fit the mold, meaning like tigers. Like there's Amur tigers, there's Bengal tigers, and there's Sumatran tigers. There's subspecies. Elephants. There's Asian elephants and there's African elephants. They've been separated and they have regional adaptations. Humans, though, we intermix so much that we don't really have that anymore. Maybe we did in the past, but humans, you really can't argue not compared to other animals. We don't really have subspecies like other animals do. So, but many people believe this, and here in the United States, we sterilize 300,000 women of Puerto Rican descent, and the idea was because of eugenics. So we are not, and this is in the 1950s and 1960s. This is not like, I mean, it's before I was born. I think, am I the oldest person here? I'm 40. I guess I am. Okay. So before we were all born. So, but still, it's relatively recent. There's a famous Supreme Court case, Loving versus Virginia. That was that threw out what are known as the miscongenation laws. So miscongenation, different species or different genuses. So the idea was that white people could not marry non-whites, and the Lovings were a white male, black female, and they got married in Washington, D.C., but they lived in Virginia, and they were arrested because of these laws. And well, at first they just said, all right, we'll live in D.C., but then They had family in Virginia. They came back, and then they were eventually arrested again. It went to the Supreme Court, and the court ruled it, okay, we need to get rid of these laws. They're not really sound. That was 1967. So I hate it when people ask, what race are you? It's human race. So, okay, but I mean, this is a science. There was a science. It's bad science, right? So this is bad science, and it can hurt people. So what makes bad sciences? Like, well, they use correlations. So you can rely on models instead of experimental data, and also consensus. When people say, do you believe this? We all agree. That means absolutely nothing. So Albert Einstein, he was and always has been really popular in the United States. He was extremely unpopular in Europe. People hated him. So the Germans hated him because he was Jewish, and the English hated him because he was German and he said that Isaac Newton was wrong. So they hated him. He was famous as a scientist, but they wanted to get rid of him. So what did he do? He came to America, and he was a professor at Princeton, right? And we still love him. People have pictures of him on their walls, right? And then, like, has that whatever face, the famous picture of Einstein. But when he put out his theory of relativity, there was a movement. It was something like 10,000 scientists against Einstein. His response was, it would only take one, meaning that it doesn't matter how many people think something. It's what the data says is true or not. So, okay. And we gotta change. How are we doing? Sorry, anybody have any questions? All right, we're gonna change topics because we changed topics quite a bit. So, in the beginning, don't worry, you're gonna be, and it's not gonna be as much as me, just talking at you guys. So don't worry, you'll be talked at less and less as the semester goes on. But we have states of matter, solid, liquid, and gas. So this is kind of a bendy. I'll use my cell phone. My cell phone's a solid. Means it has a set shape and a set volume. And the shape of this is kind of a rectangular prism. Volume is 50. Somehow I turned the camera on. All right. About 50 milliliters or something like that. So set shape, set volume, or defined shape, defined volume. This is not clear, but this has water in it. Water's shape right now is that of a cylinder. Its volume is half a liter. What's the new shape? Well, it's a cylinder, like half a cylinder this way. Volume is still half a liter. So liquids do not have a set shape, have an undefined shape, but they have a defined volume. So their volume is set. So if I were to take some water and pour it into another container, say I was like making pancakes and said, put a cup of water in there. If I poured a cup of water and then I poured it into my mixing bowl, I'm thinking like, oh, it's a liter of water here, it's a liter of water here, a liter of water here. I don't think, oh, the volume's changing. No, the volume does not change. So liquids have a set volume. Gases have neither a set shape nor a set volume. And also, gases are compressible. Liquids and solids are not very compressible. You can compress them a little bit, but that's the idea behind hydraulic lines. Has anyone ever gotten airlines in his or her brakes? I have. So if you get air in your brakes and you push on the brake pedal, first of all, it goes right to the floor, and then your car doesn't brake as much. So what do? You bleed the lines, and you can push the air out that way. So, but your brake system is a hydraulic line. So meaning when you push on your brake in your car, it carries the force of your foot pushing down on the brake, and it carries it to your rotors, and you have calipers, and it squeezes the rotors, and then you have great brake pads, and the friction along the rotors is what causes the car to brake. So, but the brake line pushing on the brake fluid is a hydraulic line that makes the calipers pinch. So, Solids and liquids are known as the condensed phase, and gas is called the vapor phase sometimes, because there's a lot more matter in the solid liquid phase. Some people ask, well, what about plasma? What's plasma? Plasma is a gas. By this definition, plasma is just an ionized gas. So let me show you some pictures here. You guys are being very attentive. I appreciate it. Hopefully it's not too boring for you guys. Listen to the melodious sound of my voice. So here's solids, and solids have a very set structure. There's two types, crystalline and amorphous. So crystalline means a regular pattern, amorphous means an irregular pattern. For instance, this is an aluminum bottle. The surface that you're looking at is aluminum oxide. Another name for aluminum oxide is sapphire. So what's the difference between the sapphire that's on the surface of this bottle versus the sapphire that you can buy in the jewelry store? Well, the stuff here is amorphous. It's a regular pattern. The gemstones, they're crystalline. They have a very beautiful pattern. This is a diamond, a picture of a diamond, and it's got the zinc blend structure. It's a tetrahedral structure. It's different than sapphire, but you can see it's a continuous pattern. So here's solid, has a very set structure. It's very ordered. Liquid is less ordered, but it still kind of hangs around each other. And gases, they just fly off. So more next semester, we're going to talk about intermolecular forces, forces between molecules. And solids have pretty strong forces. So water is actually like a V. So here's ice. And temperature means average kinetic energy. So higher temperature means more motion. So here's ice. As you heat up ice, the molecules start to go back and forth. You get to a point where the ice melts. Now it switches around. There's still attraction, but then it heats up more and more and more, and then it flies apart. That's the boiling point. So a melting point and a boiling point is a direct measure of how much attraction there is within or in between molecules. So, and we'll talk about that more later. And also, we'll learn about something called entropy. Entropy is disorder. This is very ordered. This is very low entropy. And gases are very high entropy, very high disorder. So that roles a lot of how things work. We'll talk about that later. Okay. And now, changing topics yet again. How are we doing? Anybody have any questions so far? Everyone good? Okay, changing topics yet again. I like to explain this both forwards and backwards. So most everything we see are heterogeneous. Let me move in. Are heterogeneous mixtures. So hetero means non-uniform, means different. Homo means uniform or same. So most everything we see are heterogeneous mixtures. Has anyone ever seen milk from a cow before? Like directly milk from a cow? What do you have? What's it like?
It's like thick and chunky. My hair is
Thick and chunky. So if it's chunky, it means it's not uniform, right?
Yeah.
Yeah. What about it? The difference between that milk and the milk you buy in the store? It says pasteurized and homogenized. Yeah. You can call it homogeneous or homogeneous. Both of them are correct. Homogeneous is more of a British kind of saying, but people say it both ways. So homogeneous. So you can take heterogeneous mixtures like milk, and you can homogenize it to make it uniform. So, and milk has some pure substances in it. So you can take mixtures and you can turn them into pure substances, and pretty much everything in milk is a compound. So in milk is water. That's 2 parts hydrogen to 1 part oxygen. Calcium phosphate is a mineral in milk. So calcium, phosphorus, oxygen. There's whey, that's a protein. There's various other fatty compounds that you find in milk. All of these are compounds. Compounds are a combination of elements. And so you can take compounds You can break them apart into elements. And if you have elements, so let's say I had, this is an Apple Pencil. Let's say it was a piece of carbon though. I could break it in half, then break that piece in half, then break that piece in half. I would get to a certain point where if I broke that element in half, it would no longer be that element. So if I took a carbon atom, I can break a carbon atom in half. Actually, it'll turn into 2 lithium elements. But that ultimate part of an element, that's an atom. So we can get to an element, and it gets to its ultimate part, and that's an atom. Okay, so I told you I would start and break it down, and I would build things back up. So let's talk about elements for a second. We know of 118 elements. So we know of 118 of them right now. And about 90, depending on whom you ask, it's a matter of opinion, how many of them are naturally occurring on Earth. So we have elements, we have 118 of them, and we can use those together to form compounds. And elements and compounds are pure substances. We can mix them together. If we mix them together, if it's a uniform mixture, that can be homogeneous or homogeneous. We have another name for homogeneous mixtures. They're called solutions. So solution is homogeneous mixture. And then if it's not uniform, it's heterogeneous. So we're heterogeneous, right? Our teeth are different than our toes, right? And pizza is a heterogeneous mixture. So, but tea is a solution, homogeneous mixture. So, okay, and with elements, you don't need to make compounds. You can make heterogeneous mixtures even with 2 elements. So iron and nickel. There's some meteorites that are an iron-nickel. You can get a little bit of iron dissolved in a lot of nickel dissolved in a little bit of iron. I have a ring that has it. It's a meteorite ring, and it's just 2 elements, nickel and iron, and it's not uniform. That's really pretty pattern on it. So just 2 elements can make a heterogeneous solution, or mixture, excuse me. Also, not all solutions are liquid. Air is a homogeneous mixture. It's just gases. And things like 14-karat gold. That's a mixture of gold, silver, and copper. So, and that's a mixture. That's a solid solution. So there's several. Okay, and so 118 elements. You're like, well, that's not that many. But how many letters are there in the English alphabet? 26, yeah. So 26 letters. And if you combine letters together, they can change their properties. Like the letters T and the letter H, you bring those together, it's a th sound, and then it changes the sound of the letters. And think of the words of letters as compounds, and think of the mixtures that are formed from compounds to be like stories. So how many stories can you tell with 26 letters? I mean, infinity. How many stories can you tell with 118 letters? Yeah, bigger infinity. Infinity plus Chuck Norris. So, and let's look at some of the elements. Here is the periodic table. And well, oh man, this is not as fast here. But looking at this, most of them are metals. We'll cover more next class. But most of them are metals, and most of them are kind of silver looking, right? So if you just look at the pure elements, but about 1/3 or so of humans are allergic to nickel. So many people can't tolerate nickel. Maybe you've seen people with belly button rings that are all inflamed. It's probably from a nickel allergy. And but if you combine nickel, here's nickel and titanium, where titanium's right here. If you combine nickel and titanium together, everyone can tolerate that. Well, not everyone, at least most people. I'm sure maybe there's someone that can't tolerate that. But I had braces put on later in my life because my wisdom teeth came in impacted, and it changed my teeth, and I had to get braces put back on. So I'm the lucky person that got braces twice. But because I'm a chemist, I was asking my orthodontist, I'm like, oh, what metal are you putting in my mouth? He goes, oh, nickel titanium alloy. I'm like, oh, do people get allergic to that? Because a lot of people are allergic to nickel. He's like, nope, mix them together, they're fine, people tolerate it. So that's an example of two letters, like S and H coming together to form a whole new sound. So nickel titanium coming together to form something completely different. That's really indistinguishable from both nickel and titanium. So that's one of the weird things about chemistry. Okay, so you get this, we can take elements, we can make compounds, and we can mix them together to form uniform and non-uniform mixtures. Or we can take non-uniform mixtures, break them apart into uniform mixtures, and then break those down to compounds and elements. And you get to a point with an element that you can't break it down anymore, and that's an atom. So, does everybody get that?
What does uniform mean? Like, what is the proper?
Uniform, it means that like if you take a sample from the top or the bottom or anywhere else, it's going to be the same, right? So if I have homogenized milk, if I take a sip from the top and I take a sip from the bottom, or like with a straw, it's going to be the same. But then if I take milk from a cow, it's going to be really creamy and chunky up top, and it's going to be a little more liquidy in the bottom. So that means it's non-uniform. Other questions? Okay. And we are changing topics yet again. So, physical properties. You observe physical properties without a substance change, and chemical properties you observe by change in its composition or lack thereof. So, to give you an example of this, we have in our culture the idea that if you put something around your finger, it's a remembrance of something. So that's also why we give rings for remembrance of a promise. So let's say that I was going to, I guess I did already, but propose to my girlfriend. And I say, darling, I love you. My love for you is as strong as iron. And because of that, I present you with this iron ring to wear upon your finger. So why is that funny, though? What's wrong with iron? It rusts. We pick rings based off of their chemical properties. Gold is not the most valuable metal. Platinum is more valuable, but the metal indium is more valuable than gold. Probably the most valuable metal is weapons-grade plutonium. So why don't we start giving people rings made of weapons-grade plutonium, other than the fact that it's radioactive and toxic? So you could probably mix it with something, right? You could have a little lead-coated weapons-grade plutonium ring we give to, why don't we do that? Because it's physical properties. It's the chemical properties. It's chemical properties. Gold doesn't rust, and we thought it was magical because of that. Iron, of course, gets flaky. That might be a better example. Honey, here's an iron ring, so you got to take care of it and look after it. Otherwise, it'll get flaky and fall apart and disappear, just like me. No, that would be a bad idea, probably. Okay, but let's go back and talk about physical properties. You find without changing the substance, and chemical property you change by changing substances or by their unreactivity. So noble gases, for instance, like helium, are very unreactive. So physical properties, so color is one. You can observe my shirt today is black. And you observe that, and it's still a shirt. It's still cellulose that's dyed. What happens, so this shirt is also flammable. What happens when you observe the flammability of the shirt? Well, it's no longer cotton. It's now something else. It's carbon dioxide, water, and ash, right? So you've changed, by observing the chemical property, you've changed the composition. So, and changes of state, so solid, liquid, gas, are considered to be physical properties. So if you take water, solid water, H2O, ice, You can melt it to form liquid water, you can boil it to form water vapor, you can condense that down to liquid water, and you can freeze it back to ice. It's always H2O. You're not changing substance. So melting, freezing, boiling, all a physical change. So, and here are some pretty pictures.
Can you explain the magnetism bit?
So magnetism, that is you can observe something's magnetism without changing the substance. So I can take a magnet and put it on the refrigerator. I can observe that. There's a test called magnetic susceptibility. You can take salts and you can put it into a magnetic field and you can look to see how things change. Also, an MRI. MRI is magnetic resonance imaging. What you're doing in an MRI machine is that you are aligning the hydrogen nuclei to a magnetic field, and you're blasting with radio waves, and you're changing the magnetic field. And doing all that, observing that, you're not changing. MRIs are safe. I mean, they're loud. Has anyone having an MRI? They're loud. Yeah, I hate them because I've only had 2 in my life. Hopefully, it's only 2 I have to do. But they put you in a small tube, right? And then you hear this ka-chunk, ka-chunk, bah, bah, ka-chunk, ka-chunk. They're moving magnets as they chunk, chunk. And then it's radio waves. You're being blasted by radio waves. So you can observe something's magnetic properties and it doesn't change it. So it's not a chemical change, it's a physical change only.
Is that like how you can magnetize certain metals, but that metal can also not be magnetized?
Well, there's a couple things. I have a bad habit of giving a dollar answer to nickel questions. So there's only 2 metals that are known as ferromagnetic, and that's nickel and iron at room temperature. You can get to a certain point when it's really cold. It's called the what point? It's not the Fermi point. It's the Curie point. I forget the name, but metals that are really cold can go from paramagnetic to ferromagnetic at really low temperatures, like a few kelvins. So that can be temperature dependent. And then if you change from paramagnetic to ferromagnetic, or ferromagnetic to paramagnetic, it doesn't change the metal at all either. You can also, for metals, if you run a current through it, it'll create magnetic fields that go, if the current's going this way, it's this direction. That's from the electrons going through it. And then the field lines are from the electrons. As far as bulk metals, though, you're only going to see permanent ferromagnetism in iron. I'm sorry, it's 3. Iron, cobalt, and nickel. So those are the only ones that you'll be able to see that permanently get a magnetic ferromagnetism associated with it.
But you can magnetize other types of metals, is that?
Temporarily.
Like copper wires or something?
Well, what do you mean by magnetize? You mean like for an engine?
Like it gives it like it has a magnetic field or
If you run current through it, you can. Yeah.
Okay.
Yeah. But
and that's considered a physical property?
that would be a physical property, yeah. So, all right. Is that all you needed, or?
Yeah.
Sorry, I gave you a long explanation. Other question? Are you a question?
No.
Okay. All right. Okay. So going back to physical change only or chemical change. So what I mean by physical change only, frequently when there's a chemical change, there's a corresponding physical change. So like digestion is a chemical change. So you eat broccoli, it's green, and when your body is done digesting it, it's no longer green, right? So color is a physical change. But the question is this a physical change only? So dry ice here, solid CO2, and can sublime to CO2 vapor. This is a physical change only. This is no chemical change, it's still CO2. Sugar dissolved in water. This is sucrose, sugar. You can put it in water, and it's now dissolved in a mixture, but it's still sucrose, it's still table sugar. It hasn't changed. But you have here's propane being burned, This is propane to start off with, and now it's carbon dioxide and water. So this is a chemical change. So the top two here are physical changes only, and propane burning is a chemical change. Now it's a new compound. Make sense? Okay. So, and this is, I mentioned before, that capital delta, that means change. So this is the Greek letter delta. So Greek alphabet, alpha, beta, gamma, delta. That's capital delta. Lower delta looks a lot like our lower d. That usually means partial or incremental change. So this means big change. And little delta means partial change. So determine whether each change is physical or chemical and what kind of property is demonstrated in each case. So evaporation of rubbing alcohol. So have you ever done that? Put rubbing alcohol on your skin and it evaporates, feels nice and cool. That's a physical change only. So it evaporates. Burning of lamp oil. That's a chemical change. So it's similar to the propane example. You're forming a new compound. Bleaching of hair with hydrogen peroxide. This is a chemical. So you are reacting with the proteins in your hair, more like the dyes. We have natural dyes in our hair. We have melanin and pheomelanin. Depending on your hair type, you have more of one or the other. So the hydrogen peroxide bleaches it absorbs carbon dioxide from the air, then it bleaches the dyes in your hair. And formation of frost on a cold night, that is a physical change only. So formation of frost is from the deposition of water vapor to solid ice. And you can see this in your freezer. So like every once in a while, I suddenly decide I want to start eating peas and rice. I'll buy one of those huge bags of peas at Costco. And then like 3 months later, when I finally open it, it's like a snowball with some shriveled up peas in it. What's happening is that the ice and the peas are subliming out and then they're depositing back in. So it goes from solid to vapor back to solid. That's the freezer burn of sorts. So you can desiccate your stuff that way and frost forms on the outside. So if you're wondering where that all comes from.
So you can go from a gas to a solid?
Yeah.
So it doesn't have to go gas, solid, gas, liquid, solid?
No. It's temperature dependent, and sometimes you can skip the steps. So you can see it in your freezer, and certain places, certain times, there is no liquid phase. So carbon dioxide doesn't have a liquid phase till about 3.5 times atmospheric pressure. Then it can have a liquid phase. So, okay. And, all right. Any questions so far? Changing topics yet again.
Catching whiplash.
Huh? Whiplash? Yeah, I know. Sorry. It happens quite a bit these first couple classes. So energy. We're talking about energy real briefly. Energy is defined by the capacity to do work in chemistry class. Physics has a better definition. The physics definition is this. It's the integral of the force vector dotted with the path. So it's the force times the path length. So this is, in my opinion, that's the better definition of energy. But if you study physics, like a joule is the amount of energy it takes, so this is more than a Newton, but if a force of 1 Newton over a meter, so a joule is a Newton, force of a Newton at a distance of a meter. So a force times the path length. And we have a couple of forms of energy. So potential energy, kinetic energy, and electromagnetic radiation. So question, what type of energy is chemical energy?
Potential.
It's potential, yes. So chemical energy is potential energy. When I eat that donut, I can turn that donut into kinetic energy. Well, thermal energy is also kinetic energy, actually. So it's just thermal energy is kinetic energy on a molecular and atomic level. So, of course, I could turn a donut into kinetic energy, but it's usually is turned into, more Netflix or something like that. I'm not that much of a couch potato. I'm really not. But one of the classic examples, so kinetic energy is the energy of motion, and potential energy is stored energy. So if I have a book and I let it go, right, this stored potential energy has turned into kinetic energy. And I don't want to slam it down. Everyone's awake.
I thought you were going to.
No need. So it's also the gravitational potential energy. That's how your water works, right? So we put water tanks up really high, and when you open up your faucet, the faucet is just a valve, and the water pressure from gravity just pushes the water down. So real easy. Turns it into kinetic energy. And I mentioned forces, so I want to talk about forces really briefly. There are what's called 4 fundamental forces, and I've also listed 5 there, so just to make it more confusing. But the 4 fundamental forces used to be gravity. It's still a force. Gravity is the weakest force. It is very slightly positive, and it's all matter and antimatter with antimatter and matter and antimatter feel this very positive small force. Antimatter is just matter with opposite charge and opposite headness of spin. But that's above and beyond this class. We're not going to talk about antimatter unless you want me to talk about antimatter, because I think it's cool. But we're going to deal with just plain old matter. But gravity is very positive, felt by all matter and antimatter for each other. Electromagnetic, this is that that unlike charges attract and like charges repel, and magnetic fields cause things to spin in one way or the other. That's electromagnetic force. And then we'll learn that atoms are made of protons, neutrons, and electrons. The nuclear strong force is the force that binds the nucleus together. The protons and neutrons feel it for each other. It has to be stronger than the electromagnetic force because protons are positively charged. And the nucleus is trying to blow itself up with all the positive charge, but then the nuclear strong force brings it back in to keep it together. And neutrons and protons are made of smaller particles called quarks, and what bind the quarks together, the nuclear weak. It turns out the nuclear weak force and the electromagnetic force are the same. So you could argue that we only have 3 fundamental forces. But then there's also dark energy. So from what we can tell, the space and time started about 14 billion years ago with a great expansion event we call the Big Bang. And so you had the Big Bang, and you would expect the universe to expand like this. The universe is actually expanding like this. It's accelerating as time goes on. And we don't know why it's accelerating, so we say it's from dark energy. But we really have no idea. That is our way of saying we have no idea what's going on. So we're just going to give it a mysterious name. So, but there are the 4 forces. So, or 5, or 3. So, questions so far? Changing topics yet again! Yay! Okay. So the next thing we're talking about is the metric system. And if this wasn't the United States of America, I probably wouldn't have to talk about this at all. Because England does it a little bit too, but we're kind of the weird ones. We use Fahrenheit instead of Celsius. We use feet, inches, and miles instead of kilometers. And we use gallons instead of liters. But, I still think, even though I'm a scientist, I can do both, but certain things, like colloquially, I think of Fahrenheit. And Fahrenheit was actually meant to make more sense for humans. Because 100 degrees was supposed to be body temperature. And, but of course, it's 98.6, depending on the person, right? That's body temperature. But the metric system was engineered, and it was based off of water and various other things. We've changed our definitions for the metric system now. And we have a couple base units, and then we have other derived units. I'll show you some of the derived units in a second. We still use all of these except for candela. No one really uses candela anymore. We usually use energy as light. So we say watts. This is a 30-watt light bulb. No, it's a 60-watt light bulb, right? We give it in energy. Power, watts is energy divided by time. So length, meter. So a meter is about this long. Used to be a distance. I think it was like from a city in France to the North Pole or something like that. But now we actually define meters and time the same way. So we define a second and a meter together. Luckily, everyone actually agrees on time. Can you imagine what life would be like here if we didn't agree on time? So, I mean, everyone does seconds, minutes, hours, and days, and years. We all agree on that, right? There's no one says, like, oh, you know, I'm a nerd. I watched Voltron, and they have something called a tick. That's a different time unit. So, what if we had ticks and seconds? You know, that would be hard to communicate with people that way. We also have a lot of this based off of the Babylonians. So they like the number 60. So 60 seconds in a minute, 60 minutes in an hour. That's from our Babylonian ancestors. And okay, so meters and time are defined together. Temperature. This is based off of water. So the freezing point of water at 1 atmospheric pressure is 0 degrees Celsius, and boiling point is 100 degrees Celsius. So that's based off of water. And Kelvin is the absolute temperature. We'll talk a little bit more about temperature later. Mass. So mass and the mole, these are likely to change in the next 10 or 15 years. So right now, well, a kilogram used to be based off of water. So a cubic deciliter. So deci is 1/10. So decimeter. Sorry, a meter, 1/10 of a meter is a decimeter, and a cubic decimeter is a liter. And a liter of water weighs a kilogram. Or a cubic centimeter, so 1/100th. A cc is also a milliliter. That is a gram. So
Didn't they recently change like what they base the kilogram off of?
they're talking about it. Right now, the kilogram is based off of a hunk of platinum. Unless it happened, I didn't notice.
I think I read something.
Yeah, they want to change it to silicon. They have these spheres of silicon. A mole is also, it's 12 grams of carbon-12. They want to change the kilogram and the mole to be based off of silicon rather than a hunk of platinum and carbon. So, but who knows when that's going to be changed. But is that what you heard, or?
I think so.
Yeah, I don't think it was formally changed yet, though.
Yeah, I read it in passing a couple months ago.
Amp is a charge of a coulomb per second. So in my mind, the coulomb is more important than the amp, as far as, or ampere. That's more important for this. Yeah, no one uses candela. Okay, and now we can also take these and we can derive other units. So for instance, see here. So force is mass times acceleration. So a Newton is equal to a kilogram times a meter per second squared. So that's a Newton. A joule, I told you a joule is a Newton meter. Kilogram meter squared per second squared. And a watt, so if you want to know what a watt is, it's a joule per second or a kilogram meter squared per second cubed. So a watt is mass times length squared divided by time cubed. So that's power. So that's more physics. So you don't have to worry about that too much. You have to worry about a joule being here a little bit, but we'll cover that later. Also with the metric system, you can take just a base unit and then you can magnify it like a meter. For instance, we can go really small with a picometer. A picometer is 10 to the minus 15. Jeez. It's harder to write this close. Minus 15. and an atom is usually somewhere between 50 and 100 picometers. And so you can describe atoms by using a really small descriptor here with a pico. And then humans are usually somewhere between 1 and 2 meters in length, kind of thing. And then you can have really big objects like celestial objects you can describe. And so I did this last class. I know the Earth is about 8,000 miles. That's 1.6. That's about 14 megameters. So the Earth is about 14 megameters in diameter. So you can use the same term, right? Meter to describe an atom, a person, and a planet, just by changing the prefix in front of it. And the prefixes are all factors of 10. So it makes it really easy to describe something. Okay. So you good with that? Questions? All right, and then we have density. But this illustrates a different type of property. We have intensive properties that are independent on the amount of something, or extensive properties that are dependent on the amount of something. So density is mass divided by volume. So is the density of water in this bottle, is it any different than the density of water in Lake Tahoe in California? It's a big lake, if you don't know what that is. Is it any different? No. Assuming it's all pure water, the answer is no. Density is not any different. What about the mass? Yes. Yeah. So density is intensive, it's independent of the amount. Extensive, like mass, depends on the amount. Volume, mass, that depends on the amount. So concentrations are also independent of the amount. So lots of ring stories with this class. A man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size, so he decides to determine its density. He finds its mass to be 3.15 grams, and then finds its volume to be 0.233 cubic centimeters. Is the ring made of platinum? So you have to get the density. The density is just mass divided by volume, so 3.15 grams divided by 0.233 cubic centimeters, and you get, you can see it right there, 13.5. Is this ring made of platinum? And the answer is no, because platinum's density is 21.4 grams per cubic centimeter. So this person, someone was deceived somewhere. There's a story about this, Archimedes. So Archimedes, I believe he was Greek, but the king was wondering, he gave some of his gold to a goldsmith to make a crown. He got the crown back, and the king was really worried, like, is this crown really made of gold? Did I get gypped? Because 14 karat gold looks like 10 karat gold, looks like 8 karat gold, looks like 24 karat gold. It looks all the same. And so the king was upset and asked Archimedes, like, Archimedes, can you figure out if this is made of gold? And allegedly, Archimedes, when this was in his bathtub, and as he was thinking about it in the bathtub, he realized, oh, I could look at the displacement of water, and then I could calculate the density, and I could determine whether it's pure gold or not. And he apparently was so excited, he ran to find the king out of the bathtub without dressing himself. So I guess even back then, some really intelligent people were airheads.
What was it called though?
I think the story was it wasn't. I don't remember. I have to check it out. But they found the oldest joke book or something like that. It was in cuneiform, and it actually was ripping on intellectuals. It was a series of jokes like it was like an intellectual went to go visit his sick friend, and Upon his house, his wife said, "Oh, I'm so sorry, but your friend has departed." And the intellectual goes, like, "Well, when he returns, let me know. I'd very much like to speak to him." The idea, that smart people can be dumbasses. I gotta watch what I say. I'm being recorded. Not yet. I need to watch what I say because I can be a total airhead sometimes. Alrighty. Are we good? Time to change the topics yet again? All right, so the next thing we'll talk about is significant figures. So when we look at measurements, we have to have a way of knowing how valid, how much we know something. So on one of the Apollo missions, we put a mirror on the moon, and about 4 times a day, they shine a laser at the moon, and they measure the distance very accurately between the Earth and the moon. And what they found out is that every year the moon has been moving about an inch away further from the Earth. So the moon is slowly moving away from us. And this can also supports the theory is called the Great Collision. We believe that the moon was created by a collision in the early solar system, that a planet about the size of Mercury collided with the Earth, and that's the reason why the Earth is tilted on an axis, is from that collision, and that then that vaporized the surface. Well, it melted the surface of the Earth, and then ejected a bunch of material, and that formed a ring around the Earth, and that congealed to form the moon, and explains why there's materials on the moon that are like the Earth, but there's also stuff that's not like the Earth. And the moon is also tidally locked to us, which means the same face of the moon faces the Earth. And we believe what happened was, after the collision, that a day was on the order of 6 hours long, and the moon was much closer. But since we have oceans, it creates drag. So as the moon is orbiting, that's also where the tides come from. And that's causing the moon to slowly move further and further away from the Earth. Eventually, the Earth and the moon will become tidally locked with each other. And so the same face will always face the Earth. And at least that's what we think. And so that explains, and our days are getting longer. So days are getting longer, and the moon is going further away. But part of the reason why we think we know that is because we continually check the distance, about 4 times a day. So that's a very, very accurate way of checking the distance. When I cover distances, I usually do it by either my step tracker on my cell phone, or I can use my car's odometer. Like, say if I want to figure out, like, oh, how far is it? Because I like to run, so I want to, like, oh, how far is my running route? So what I'll do is I found sometimes when I run with my cell phone, it doesn't work as well. Walking it in the pocket, things work better. I can walk things, or I can use my car's odometer, right? So, but there's a certain number of figures on there, and my car's odometer works to 1/10 of a mile, for instance. And I don't know about my step tracker. How many digits do I get in this one? Okay, it's asking me to update. I'll figure it out later. Why do you need to update a step tracker? But for sig figs, significant figures, so generally speaking, measurements are reported that the last digit is an estimate. So for instance here, so if we look at this number, 5.213, we're certain about these digits. The last one is uncertain. So, but we're still like plus or minus 1 digit though away. It's not like completely wrong. Let me give you an example. So let's say we're going to measure this. So let's try and measure this, and I can tell that here is 4 milliliters, and this is at 0.5. So I know I'm at 4.5, and then I kind of have to see here where I'm at this meniscus. So the meniscus is about right here, and I already know this answer because I taught this last class. It's to say at 4.57 ish. Could be 4.58, 4.57. So the idea is this number here, it's probably plus or minus 0.01 milliliters. So we can we know that this is about, we know that this is definitely 4, this is 4.5, 4.5. This one right here though, 7, 8, not so sure about that. But also with this, this is something that we're losing. We've already lost computers. So my PhD advisor, he's 80, and he was a scientist when we had a big switch over to computers taking data. I mean, now sometimes humans take data, but not really, right? Usually we have machines do this for us now. And he mentioned like, oh, it was such a big deal because some people prided themselves with how well they could gather data, and suddenly this machine did it and they couldn't keep up. So that's another thing that we're worried about in the future. People are losing jobs, right? So in 20 years, we may not need drivers anymore. We might have automated cars, all these kind of things. So what are we going to do? Well, how are we going to work? A lot of workers are going to be lost to automation. So we'll see. We've already lost this. We've already lost this to automation. We very infrequently do titrations. Usually a robot does it. So only in a very few examples do people actually do titrations anymore. And they're usually kind of rare and exotic. But why, if this is already outdated, why are we going to make you do this in Chem Lab? Well, there's two reasons for it. One of them is the purpose of the university. The purpose of the university is to preserve old knowledge and generate new knowledge. So we're preserving that knowledge. That's one of the things. The other thing is it's for education, because this way you can start learning. And a lot of people are tactile learners; they learn by touching things. So you guys are you're getting bored, huh? We still got 4 minutes.
Are you gonna have to calculate uncertainty in this class?
No.
You just did that this morning.
For okay. It's not that hard though.
No, not really.
Yeah.
It's kind of a pain in the ass.
Yeah. You're talking about like the uncertainty, and then you look at the statistical distribution of it.
Yeah. Like
Yeah.
adding uncertainty.
Physics teacher said there's no true measurement.
That's true. Well, unless it's an exact number. But we are going to talk about addition and subtraction of significant figures, though. So I don't know if you consider that uncertainty. When I say uncertainty, I'm assuming you mean you have 5 measurements, and then you have the uncertainty in each measurement, and you combine them all together. Is that what you're talking about? Okay, yeah. No, that's not in this class. So. Okay, although this is exactly where we ended at the last class, and I think I'm going to follow suit, and we ended about 2 minutes early too. So Monday is a holiday, so I'll see you next Wednesday, and I'm sorry I had to talk at you guys all class today. You might have me talk at you for a little bit longer, but then we'll start getting into some more of the interactive stuff.
You said coming to class is optional.
Yeah. So that's on what?
Everything gets done.
Yeah.
Okay, I'm going to Lahaina next Wednesday for a lab. And so
Lahaina?
Yeah.
What lab are you doing in Lahaina?
Coral reef service.
Oh, that's cool.
Yeah.